Homework 9.2 is a ramjet engine, which requires that the engine is moving for it to work. So we'd have to have some way to get this airplane flying. So all we have is a diffuser, which will increase the pressure. So that's our compress it. And then we have heat exchanger or combustion chamber in reality, but thermal will get heat exchanger. And so we have state 1, 2, 3, and 4. So the exit our nozzle accelerates it and we get our thrust. This only works if there's air flowing through the system. So it has to be moving for it to generate power. There's a number of ways we can do that. Fly it on the back of another plane and drop it off. Put solid rocket boosters on the wings, have an auxiliary system that gets it flying and then converts to this system in flight. So very much like the last problem, we just skip the diffuser or skip the compressor part. So we have, like before, isentropic process. So we have that the first law, m dot times H inlet, which is H1 minus H2 plus V1 squared minus V2 squared over 2 equals 0. If we neglect work, heat transfer, it's steady state, and there's no change in potential energy, then our first law reduces to this. Of course, again, we can divide by m dot. This becomes 1, and so I have that H2 equals H1 plus V1 squared minus V2 squared over 2. Now, in this case, I'm not going to replace H's with CPT because this is the standard method. We're going to make similar assumption as we did before that V2 is small compared to V1. So we've decelerated the flow to a much smaller velocity. So we're going to neglect V2 compared to V1 squared. And so we get H2 from that. Of course, we need to find H1 first. So this time, though, we find H1 is a function of T1 from the ideal gas tables. T1 is given as 230 degrees. So we can find the enthalpy and PR for state 1. So the enthalpy is 230.02 and PR 5 or 0.5477. So if we go back to we have 230.02 kilojoule per kilogram. That was from the ideal gas tables based on our T1. And the same thing that PR1 is going to be a function of T1 as well, which is 230, and that was 0.5477. Again, from the ideal gas tables. Now, to find the at state 2, we use our equation, which is going to then be 230.02 plus 650 meters per second. Square that. We'll have units then of meters squared per second squared, and then divided by 2. Now, we'll need to meters squared per second squared, and the units of this is kilojoule per kilogram. So we have 1 kilojoule per kilogram is 1,000 meters squared per second squared. So the meters squared per second squared cancel, and we'll end up with kilojoule per kilogram. When we do that, we get 441.27. Now we go back to the ideal gas tables, and in this case, we're going to find temperature that corresponds to that enthalpy. So now we know this is 441.27. When we find that value in the table, we'll have to interpolate, of course, and then we'll find the temperature that corresponds to that. We'll also find the relative pressure that corresponds to that enthalpy. So that same enthalpy, we'll interpolate to find P. And for state 3, we're given RC again, and RC is really a volume ratio, but it's also a temperature ratio. So T3 over T2 equals RC. So we get T2 times RC is our temperature 3. Then just like before, we can look up the enthalpy from the tables. So we have the function of T3, we can find PR3, which is a function of T3. And then we know that the pressure at 4, just like the other problem, goes back to the pressure at 1. So when I have P3 is known, divided by P4 equals PR3 over PR4. That's going to be, well, we already know it, but a function of T3, and PR4 will be a function of P4 from the ideal gas tables. And that's true because it's an isentropic process. The nozzle is isentropic, so S equals constant. And it's an ideal gas. In this case, it's not constant specific heats, it's variable specific heats. So we can use this expression just for those processes where ideal gas with constant specific heats. And then we know that P4 equals P1. And we found the pressure, well, the pressure at 3 is the same as the pressure at 2. So I guess we found the pressure at 2 from the relative pressure. So P2 equals P1 times PR2 over PR1. And again, that's because that diffuser is also an isentropic process. So we're making use of that to find our pressure. And then P3 equals P2. So really this is used here to find P4. And then we solve for PR4. So use this expression to solve for PR4. And then from PR4, we can find the enthalpy. The enthalpy 4 would be a function of PR4. And then finally, we'll find the velocity like we did up above using the ideal gas law, this relationship. So now we'll be using it to relate states 3 and 4. All right, much like the other process, the only additional term that's given here is the Q, and so the heat transfer per unit mass going into the heat exchanger would just be MC delta H. So again, using the first law, dE CV dt equals Q dot minus W dot plus M dot H inlet minus H exit plus V inlet squared minus V exit squared over 2 plus GZ inlet minus Z exit. And for process 3, 4, or actually 2, 3, which is our heat exchanger. This would be 2 at the inlet, 3 at the exit, 2 at the inlet, 3 at the exit, C2 minus C3. We're saying there's no change in elevation, there's no work for the heat exchanger, it's steady state. And so we have Q, 2, 3 divided by m dot would equal H2 minus H3. And we're also going to make an assumption that the velocity doesn't change in the heat exchanger. So that possibly can happen, but we'll say that the area is expanding as it's being heated, so that that's not true. So we're going to make the assumption that V2 is equal to V3, so this term cancels. If we didn't make that assumption, which, you know, in a real engine, it may not be perfectly balanced with the heat transfer and expansion, but we can't solve the problem without making that assumption. So it's a fair assumption, I guess, to solve it. Of course, we'd want more details about it if we wanted to be more accurate. So that's what we're looking for here, the rate of heat transfer per kilogram rather than per time. So this is just Q23 over m dot, which is our H2 minus H3. I hope that guides you through it. I know I didn't work out a lot of the numbers, but I think you should be able to do that and use the tables based on these part A through C.